Hi everybody. What follows is a little description of sigma notation. So sigma notation is another way to describe long sums. If we just consider the list of numbers like 1 plus 2 plus 3 plus 4 plus 5, then we'll use an ellipsis to indicate that this keeps on going. That's one way to write a sum going up to a certain number. And suppose we're talking about writing that sum up to, 1,000. So the ellipses, which is usually just 3 dots, indicates that there are a bunch of terms that follow a consistent pattern. And this is one way to write a pattern out like this. Another way is using sigma notation. Sigma is the capital letter from the Greek alphabet that looks a little bit like an E. So if we were to write this same exact series out using sigma notation, well, we'd be talking about some number like I that starts at a value of 1 and goes up to a value of 1,000. Now, this works a little bit like, if you're familiar with computer science, a for loop or a loop. It's essentially a program that starts us off by saying, okay, start with I equals 1. And then let I equal the next number, 2. And then let I equal the next number, 3. And it continues on and on and on in this way. Each of these terms are then added. So when we get to I equals 10, we would have plus 10. When we get to I equals 11, 11. It continues on. When we get to I equals 1,000, we're finished because 1,000 was the end of our index. So there's a start of a sigma expression. There's an end of a sigma expression. There's an expression in between, which is going to create all of these terms. And that expression is often written in terms of a variable. And it's the variable that we allow to increase from the start to the end. Each of these terms are added up. So let's take a look at another sigma expression. I apologize, the focus keeps on changing on this. We're going to use the variable n. And we're going to start at 1 and go to 10. And we're going to deal with n squared minus 1. So if we evaluate what this is, well, the first time we go through it, I'll open up a set of brackets. N is going to start with a value of 1, so I'll have 1 squared. And then I'll subtract 1. That's the first term. The next time I go through, n is no longer 1. It's now 2. So I'll have n squared, or 2 squared, subtract 1. And I'll keep going on and on and on like this. 3 squared, subtract 1, all the way up to my end, which would be 10 squared, subtract 1. Now, if I wanted to evaluate this expression, not just expanding it, because that's what we call this would be expanded form. I could go ahead and simplify each term. Well, this is 1 minus 1, 0. This is 4 minus 1, 3. This is 9 minus 1, 8. The next one's going to be 16 minus 1, 15. And so on and so forth, all the way up till we get to 10 squared minus 1, which is going to be 99. And we can add up all of those terms. You'll have to forgive me. I'm going to use my calculator for a second. I don't have that one memorized. and we get to 375. Now, I fortunately have a really cool calculator in that I can type in exactly this expression. Now, I didn't use the variable n, I used the variable x, but I have the same expression, my variable squared minus 1. And my calculator can type this out and work with it. Yours might as well. So that's the basics of sigma notation. Let's take a look at a couple of cool sums. Instead of using n, I'm going to use the variable I. And I'm going to let it go up to another variable, n. Now, what I'm going to do is I'm going to deal with i's. I'm just adding all of them up. So my first term goes from 1, and then 2, and then 3. And we've seen this before. This is the first expression that I had. The only difference is, instead of starting at 1 and going to 1,000, we're going to start at 1 and go up to n. Now, this expression here is a little bit more difficult to add. But what if we expanded it and added a few more terms? Well, the second last term would be n minus 1. So the third last term would be n minus 2. Then we would have n minus 1. And then we would have n. If this went up to 1,000, this would be 1,000, this would be 999, and this would be 998. We can actually add all of these up in a fairly unique way. If I just pair up the first and last term, I would have n plus 1. Now I'm going to pair up the second and second last term. That would leave me with 2 plus n minus 1. And I'll continue doing that. So the third and the third last term. So that's 3 plus n minus 2. And now I'll have to keep doing that. Now because there were n terms in total, when I pair them up like this, I have half as many terms. So in actual fact, that means that in all of these, including that ellipsis that goes on forever, there are n over 2 of these pairings. So let's take a closer look at these pairings. Now simplifying the first one is easy, it's just n plus 1. Same for the second one. I'm going to bring the n in front, and then 2 minus 1 is, would you look at that? They're the same. Well, let's take a look at the third. Perhaps it's different. I'll bring the n to the front, and then 3 minus 2 is, the same. And I suppose it's going to be the same for every other term in this ellipsis. Now, since there were n over 2 of those pairings, that means there's n over 2 of these n plus 1s. Well, if I have 3 2's added up, that would be 2 plus 2 plus 2, or 3 times 2. But I don't have 3 2's. I have n over 2 n plus 1's. So I have n over 2 times n plus 1. And this is the formula for the sum of the first n whole numbers. I should say natural numbers, not whole numbers, as we didn't include 0. Another interesting one is the sum of the first n squares. Now, we can go ahead and determine this, and it turns out to be n times n plus 1 times 2n plus 1 over 6. Now, the process that you use to determine this involves solving linear systems, it also involves finding constant third differences, and it also involves just being pretty good at algebra in general. So this is a rather, well, I wouldn't say too complicated, but it's a slightly more complicated proof than I want for this video. But this is a common sum. Often we want to see things like, okay, what is the sum of all of the squares minus some number? And that can be dealt with in another way. So this is one of our special ones, and this is another one of our special ones. And we should perhaps know explicitly these two. So that's I goes from 1 to n of I, and I goes from 1 to n of I squared. So we have two formulas that we ought to know. Now, just a couple properties about sigma notation. Suppose I have a sum, again from 1 to n, of some set of numbers like a to the power n plus bn. Well, this means that I have my first term being a1 plus 1b, my second term being a2 plus 2b, my third term being a3 plus 3b, and so on and so forth. Well, because addition is commutative, I can actually go ahead and write this as a1 plus a2 plus a3 plus a4 plus, and that goes on forever, or to n rather. And then I would put in my b terms. I would have 1b plus 2b plus 3b, and that goes on until we have our nb's. Well, now I can write each of these expressions in sigma notation as well. So this would be sigma goes from I equals 1 all the way up to n of a to the power n. And this portion would be sigma goes from I equals 1 all the way up to n of nb. And because I'm adding these two portions, I'm adding these two notations. So what can we take from this? Well, we can take that sigma notation is distributable across a set of terms. Meaning, much like FOIL or distribution when we multiply a monomial into a binomial, we can multiply this sigma in to create our first, multiply this sigma in to create our second. Now that works regardless of whether this is positive or negative. Because if it was negative, these would just all be negatives. That would mean that all of these would be negatives. And that would mean that really we could common factor out a negative. So regardless of whether it's positive or negative, that property holds. So you can distribute. Now that should be enough to get you started on using some sigma notation. If you have any questions, please feel free to email.